Okay, so then the next thing that we're going to look at, the next integral, is not integrating ln. We need a little bit more calculus for that. Right now we can't undo the natural log function, but what we are going to do is do a integral whose antiderivative is natural log. And it's a really cool thing. You could actually graph. You could graph the function and measure derivatives on, like, let's say Desmos or graphing calculator, and you find out that the relationship, well, actually, we saw that from last chapter that we know the derivative of ln, right? So if you were to graph that and you use limit definition or whatever, we know that the derivative of ln is equal to 1 over x. But now I have this antiderivative, like, why do we need an absolute value? Because think about the natural log function. The natural log function is only defined when it's positive. But 1 over x is defined like positive or negative, just not 0, right? So like our 1 over x function looks like this and looks like this. And so since the domains don't match, if we are starting here and going backwards, so if I say here, let's go backwards, then we need to just account for the fact that we need to be able to have the domains line up. So that's why we have that absolute value there. So just to match up the domains. So why does the antiderivative need absolute value? To, I guess, accommodate the domain of 1 over x. Okay. And so for both of them, it can't be 0. You can't divide by 0. You can't take the natural log of 0. But if you do ever have a negative, just make it its positive value. So like example 1, so then we integrate 4 over x. So that's the same, you could say it's the integral of 4 times 1 over x dx. Because once we've identified that function, we know it's the natural log of the absolute value of x plus c. Now, there's so many things you can do with logs to, like, make equivalencies. Like, one is you could bring that 4 up, and you could say it's a natural log of the absolute value of x to the 4th power plus c. And since x to the 4th is already positive, then you wouldn't necessarily need those absolute values. So any of those answers would be fine. Okay, but definitely watch for chain rule. So, like, this is a reciprocal, all right? So but it's still not just an x. So I'm still going to use a u substitution. So let's let u equal 3x plus 8. Its derivative is 3 dx. And so we are off by a factor of 1/3. So now I can rewrite this as the antiderivative of 1/3 times 1 over u du. And then that's 1/3 natural log absolute value of u plus c. And then go ahead and rewrite u in terms of x. So that's 3x plus 8. And, again, if you wanted to write an equivalency, if you didn't like that fraction of 1/3, you could bring it as a power. And remember, the 1/3 power is a cube root, so that would work too. The next one, and a good reminder is that du can never be in the denominator. So you should never be picking a u in the numerator when you have a denominator like that, unless you have something specific about that function that gives you that derivative down there. So plus I know that this is quadratic, where this is linear, and a derivative takes it down a power. So it makes it, again, a good candidate for that to be my u. Let's let u equal x squared plus 4. So its derivative would be 2x dx. We have an x, so we need 1/2 du is equal to, dx. And then I'm going to eventually change everything towards u. So 1/2, and there's my du. And now it's 1 over u. And then 0 becomes 4. And 2 becomes 8. And now I no longer have to deal with the x's anymore. And then the antiderivative, so it's 1/2 the natural log of absolute value of u. And then instead of putting a plus c, I can say a 4 and an 8. So it's 1/2 natural log of 8 minus 1/2 natural log of 4. And notice I don't have absolute value anymore because 8 and 4 are already positive. Now, if I factor out the 1/2, then this is natural log of 8 minus natural log of 4. And if you remember, when you have a difference of logs, you can put that together as a log of one quotient. So I guess that's 8 divided by 4, which is 2. So 1/2 natural log of 2, or if you really want to get fancy, you could say it's a natural log of the square root of 2. So, any of these obviously is equivalent. Let's say you forget about that simplifying and you leave it like this. Like, that's fine on free response. But on multiple choice, it would most likely be one of these last two. Okay, so then we get to tangent. How exciting. And cotangent, of course. And up to this point, we haven't integrated them. We've done antiderivative of secant squared, which is tangent. And we've done the antiderivative of secant tangent, which is secant. But if I want to undo tangent, the reason I have it in this section is because tangent can be written as sine over cosine, right? So it makes it a great candidate for this section. Because, and again, here's a case where they both sort of are related, so you might make an argument that I can let either of them be your u. Oh, I'm going to let sine be my u because the derivative is cosine, but you can't have a divide by du. Du has to be multiplied. So in a way, so I'm forced to make u my cosine. Its derivative is negative sine of x. Bring the negative over, so like negative du is equal to sine x dx. Oops, forgot my dx there. So now this becomes negative, the antiderivative negative of 1 over u du. So it's negative natural log of the absolute value of u, which we said is cosine of x, plus c. Now, you could leave it like that. That's fine. But a lot of textbooks, what you end up seeing is this negative actually gets brought inside. Is the natural log of cosine of x to the negative 1. And you won't see it like that. Cosine to the negative 1 means do its reciprocal, 1 over cosine, which is secant. So then I would say, okay, I can think of it as natural log of the absolute value of secant plus c. So that's probably how you would see it. And you don't have to memorize it, or you can memorize it. It's up to you. Sometimes students just remember antiderivative tangent is natural log of secant x and move on. If you forget it, you could derive it. Okay, cotangent we can derive very similarly. Cotangent is cosine over sine, and then I'm going to let u be my sine because it's in the denominator. But that also is nice because its derivative is just normal cosine, no negative, which I have right there. So now I'm integrating 1 over u du, which is just the natural log of absolute value of u plus c. And we said u was the sine function. So natural log of the absolute value of sine of x plus c. Okay. And again, same thing with tangent. You can either memorize it or just derive it. It's whatever you want. And then our last example here, just another good practice of u substitution. The expression that it has more than just e often makes the good u, because especially with this, that's going to go away when I do a derivative. So if I let this whole bottom be u, so let's let u equal e to the negative x plus 4. When I do a derivative, that goes away. It's its own derivative, but chain rule off by a negative. And we only and we actually have it up there. Wow, that just is perfect. How great. So then it's the antiderivative of 1 over u du, which is the natural log of the absolute value of u plus c, and u was e to the negative x plus 4. Now, nothing wrong with leaving it like this, but some of you might realize that this is always positive. Even with a negative exponent, it just makes it a fraction, positive fraction, that is. So if you left it like this, e to the negative x plus 4 in parentheses, you would still be okay, because again, it's already positive, so the absolute value doesn't really serve a purpose in terms of fixing the domain, because it's still already there. Okay, so hopefully okay start to chapter 5. Look at the homework, and then certainly come in if you have any questions.